Hi, my name is Joshua MacFie. I'm with Group NIRE, and I'm here to present to you on testing wide bandgap devices. The actual project that we did for Power America was the establishment of a commercial wide bandgap testing center. The key team members you can see on the screen here. So just a real quick overview of the presentation. We're going to talk about what Group NIRE is, then we'll go through the actual project real quick, the overview of tests and contact information. So a little bit about Group NIRE. We were formed in 2010 by Texas Tech University. We were formed to fill a fast test site development demand. So we were formed because the university required something that was nimble and fast to be able to set up these test sites, and it wasn't quite available in the university environment. We reside in Lubbock, Texas at Reese Technology Center, which is an ex-military base. And within this building here that you see on the right, there are two labs. There's the R&D lab where we use to develop projects, including this Power America project. And then there's the wide bandgap testing lab that we use to actually test wide bandgap devices and modules for this actual project. So the project that we've done with Power America and Texas Tech University was to establish an independent testing facility to perform reliability analysis of wide bandgap semiconductor devices. The overall objective here is to improve overall confidence in the long-term reliability performance of wide bandgap devices and modules by providing independent reliability analysis services. So we'd like to be an independent company that it could offer stuff like complementing gaps in manufacturers' own testing capabilities, provide independent testing services to verify or corroborate manufacturers' own test results, and to offer custom services to aid in determining suitability of devices for specific applications like power supplies. So the tests that we've developed for this project are high temperature operating life, high temperature reverse bias, high temperature gate bias, surge, short circuit, DIDT, DVDT, diode avalanche, switching, and TDDB. As well as a few custom things. Now, the capabilities specifically are listed per test, but these capabilities overall are up to 15 kilovolts, low voltage continuous current up to 300 amps, 1 kiloamp pulse current, temperature range from -68 degrees to 200 degrees C, and humidity from 30 to 90% dependent on temperature. So we'll give a quick overview of a lot of the tests here, starting with the high temperature operating life test. This test biased the operating nodes of the DUTs. The DUT may be operated in a dynamic mode, and we take and we vary those input parameters. They can be adjusted to control internal power dissipation in the DUT, right? And some of the parameters there are like supply voltage, clock frequency, input signals, and the like. And then the bias conditions basically bias the maximum number of potential operating modes in the device. So you'll see the circuit on the right there. It's a pretty basic circuit. When you talk about the high power that it takes to do these things, there's a lot of nuances that go into it here. Another test that we've set up for commercial use is our high temperature reverse bias test. This reverse biases the major power handling junctions of the DUT. It's operated at or near the maximum rated breakdown, so usually 80 to 100%, somewhere around there. The bias conditions bias the maximum number of solid state junctions in the DUT, and the DUTs are operated in a static operating mode. So basically we just bias it and let it sit there. And it's typically used for power devices. Now, if you go back and look at some of the previous capabilities that we were looking at, we can do this at high voltage for a high voltage, high temperature reverse bias test. And we can also do H3TRB test with the same test bed. Now the surge test, basically we've got an RLC ring down circuit designed at roughly 50 hertz. And there's a capacitor there that's charged to the proper voltage to generate the desired max amount of current output. Now the thyristor is closed to complete that ring down circuit. And then after we get at positive half pulse delivered to the DUT, then the thyristor switches open. Now this process generates a half sine pulse width of 10 milliseconds. And duty cycle can be adjusted to allow for repetitive and non-repetitive testing. Now for the short circuit test, the capacitor in the schematic on the right here is charged to the desired short circuit voltage. Usually that's 80% of the maximum DUT blocking voltage. The DUT is then switched on for a certain pulse width, and then from there we can watch VGS to see if there's degradation in the DUT. The DUT short circuit rating can be defined as the amount of energy dissipated during the short circuit event before the DUT degradation occurred. So for the DIDT test, it's conducted by switching the DUT on as fast as possible. We can change that switch on rate by changing the gate resistance. Now the capacitor bank voltage on the right and the resistor can be adjusted to control the maximum pulse current. Now special gate drivers are used for this test to drive that DUT to get the physics as close as possible to get that very fast turn on time. So for the DVDT test, which you can see the circuit on the right there, we want to get as fast a pulse as we can into the DUT. Now this fast pulse, this fast DVDT, which is usually greater than 50 volts per nanosecond, can negatively affect power semiconductor devices. For example, MOSFETs can experience uncontrolled turn on during fast DVDT events. A DVDT test bed basically generates its pulse really fast. Now, a common way of doing this, and one of our test beds is actually this, is to set up an avalanche stack and to generate your pulse that way. And that's what you see on the right there. Now for the avalanche test, we use an unclamped inductive switching circuit to conduct this test. The avalanche mode operation is induced by the unclamped load inductance. So basically you get the current running through this guy, and when you turn it off, you get a very large spike in voltage, and that can cause the avalanche. Now the drain current is increased in steps slowly until you get a device failure, and that's where we would call the end of the test. So for all these tests, some sort of characterization is associated with the test. For say a failure test, something that's going to go to failure, then you might just characterize the device beforehand to get the specs of the device and then run the failure test. For non-failure tests or tests where there weren't a failure, say like an HTRB, you would characterize the device beforehand, and then you could characterize the device afterward to see if there was any sort of degradation and where that degradation was. Some tests actually have characterizations that happen incrementally throughout the test. Some of the characterization curves that you might see are forward IV, reverse voltage breakdown, threshold voltage, transconductance, gate leakage, or internal device capacitances. Over on the right here, you see initial versus final curves, reverse and forward, of a device that we did DVDT testing on, and that device tended to do just fine with this test, and it doesn't seem like there's any degradation in the reverse and forward IV curves. Another one here is the forward IV characteristics of a 1200 volt MOSFET that we had done some testing on. So for this testing, a lot of custom equipment was required because there does not exist a very good market for this very high power testing at a very accurate level. So for this test, we've used a high voltage curve tracer that was custom up to 30 kilovolts, a high current curve tracer up to 500 amps, and we've done a lot of custom building of safety stuff, plexiglass and interlocks and ground rods, and a lot of safety stuff to keep protocols and keep people safe, and to keep the environment safe for people entering and exiting and the workers. So that does it for this quick presentation here. I know it's short, but we've only got 10 minutes. I could probably show you guys another 20 or 30 slides. If you have any questions, feel free to contact any of the names you see here. Myself with Group NIRE, Joshua MacFie. We handle more of the commercial side of things. Dr. Stephen Bain was kind of the originator of this project through Texas Tech University, and he works in the Pulse Power Lab there. And Jonathan Forbes actually is kind of a glue between us and TTU that has kind of really held this project together and moved it forward, bringing a lot of their ideas from their side of things over to us and working with us to create custom stuff that will help us move forward, as well as the whole project and Power America in general. So guys, if you have any questions, I encourage you, please email one of us. Have a great day.